Space, the final frontier. This is the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Its mission to explore the solar system, to seek out new observations and data, to boldly go where no podcast has gone before. And now the host of the Observer's Notebook, Tim Robertson.
Hi, everyone, and welcome to the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Each episode, we share the latest discoveries, observing techniques, and stories from the people who explore the moon, planets, comets, and beyond. Whether you're looking through a backyard telescope or leading professional research, we're all united under one sky. I'm Tim Robertson, your host, and thanks for being here. Now, if you usually listen or watch the podcast in your car or your phone, do you know you can now watch it on YouTube? That's right. The Observer's Notebook is now available in video right here on the ALPO YouTube channel. And here's another interesting fact. Over 50% of the people watching or listening are not subscribed. So take a quick second, hit that subscribe button and ring that bell so you don't miss any more episodes. It's free and it really helps grow the channel. The show is made possible by support from you, our listeners. If you'd like to help keep the Observer's Notebook going, check out our Patreon page at www.patreon.com/observersnotebook. For just $1 a month, you're supporting the show. For $5, you get early access for each new episode. For $10, you receive a copy of the Novice Observer's Handbook. And for $35 a month, you're listed as a producer of the podcast. And of course, to learn more about the ALPO, you can join us at www.alpo-astronomy.org, where you can join the organization for as little as $22 a year. And now, let's get started with episode 228 of the Observer's Notebook. Enjoy. All right, I'd like to welcome everybody back to this edition of the Observer's Notebook. Today we have a special guest, Daniel Parrott. He's a software developer and creator of the Tycho Tracker, one of the most powerful amateur accessible tools for asteroid detection and photometry. Daniel's passion for programming began at age 10. He taught himself C++ using Teach Yourself C++ in 24 hours. I got to hear about that. In 2018, his passion developed Tycho Tracker, which is what we're going to talk about today. It was inspired by an experiment stacking asteroid images from itelescope.net in thousands of possible motion vectors, an idea that eventually evolved in his own GPU, accelerated synthetic tracking algorithm. And thanks to Tycho, amateur astronomers have discovered over 200 near-Earth asteroids, more than 10 comets, and even 2 predicted impactors. Tycho now supports light curve generation, rotation period analysis, and variable star photometry, expanding its utility far beyond astro hunting. Daniel, welcome to the podcast.
Thank you very much, Tim, for the introduction.
Yeah. Now, when did you first recognize that programming and astronomy would intersect?
Yeah, so I began programming again at the age of 10. You kind of mentioned earlier the book Teach Yourself C++ in 24 hours. And so that kind of started. I have an older brother who was taking a course in high school, if you will, in programming, and I saw what he was able to do with it. And I thought, well, that looks pretty cool. Wouldn't it be great if I could also write my own programs and kind of, make the computer do what I wanted it to do? And so programming started off first for me. I kind of had that as a first hobby before astronomy. And then I got a telescope. And so that was, it was a computerized go-to telescope. They were all the rage.
Okay.
And they still are, I mean,
Yep.
they've evolved since then, but, these were go-to telescopes. And I thought, well, that was really cool. You could kind of just tell it where you want to go, and it would slew to the object. And then you add a camera. Okay, so now you can take pictures. And so I thought, well, that'd be pretty neat to kind of get involved with astrophotography. And so I had a little bit of experience with a science fair project where
Mhm.
I created a project on steganography, and that's where you can hide information inside pictures. And I basically just had uh, an understanding of how to manipulate pixel information. So you could, take in an image, you could load it, and then you could do whatever you want in memory with that. So I thought, well, now I can take this to astrophotography, and so that's kind of the meshing between programming and astronomy for me is those two hobbies.
So is that how the idea of Tycho Tracker started?
Well, Tycho itself started in 2018.
Hmm.
So, and before that, the inspiration, I want to say that started in 2014. Catalina Sky Survey, if you know who they are,
Oh yeah.
they're one of the most prolific asteroid discovering surveys out there. They had a programming competition in 2014. And I saw that and I participated and I learned an awful lot. This was the technique of what I call it the traditional discovery technique, where you have four images, 20 minutes apart. And so you can write a program to see if you can recognize moving objects
Okay.
in that sequence of images. And so learned a lot from that. And then, like I say, 2018, a few years later, I thought, well, be kind of cool if I revisited that topic. And what I did there was I rented some time on the service called itelescope.net.
Hmm.
So I live out in the suburbs. I have some light pollution, so I wanted to get some clean quality data. So this is an online service where you can rent time on a telescope.
Right.
It's remote, and so um, the thing is, with that service, you could not have your images spaced 20 minutes apart, like the conventional method where you take one image and then wait a sufficient amount of time for movement, take another, and so forth. So here, what I did was I just took a series of 60 1 minute images, 60 images, 1 minute exposure each. And I then uploaded that data set to others on the Cloudy Nights forum. I don't know if you're familiar with
Oh,
Cloudy Nights.
oh,
Okay.
very much so.
Yes. And so I was very fortunate. Um, I don't know if Tycho would be around if I hadn't received this feedback from one of the astronomers there. He reached out to me and said, hey, what you could try doing is you could stack those images according to the motion of the object.
Hmm.
And so I thought, well, that's kind of cool. I tried it, by the way. Um, and I did so. I wrote a really, really basic program that you give it a set of images and you tell it the motion vector of the object. So it has this speed and this position angle, and it stacks the images accordingly. I saw, wow, here's a huge improvement in the signal noise ratio. And I thought, well, what if we could take that and that same concept and apply it towards discovery? So rather than just after the fact that, oh, I know the motion of the object, what if we could try hundreds or thousands of different combinations of motion vectors? And, it seemed like a really crazy idea, right? Because stacking images is a computationally intensive process.
Hmm.
So, and then to do that hundreds or thousands of times, well, this was right at the time when I had also developed some expertise with GPU programming. And so I thought, well, okay, let me try this out. And I have a NVIDIA, this was at the time, I had an NVIDIA GTX 970 graphics card. And so I wrote up some code there to do it. And so, it turns out it could kind of actually work. Um, and so I was also fortunate that also another member on Cloudy Nights also happened to work well, he works at Catalina now,
Okay.
but he was a uh, very passionate astronomer with asteroid discovery. And so he had his own setup and everything. And, I got some great tips and ideas from him too. And he would run my program and give me feedback. And so So those are the early days, 2018,
Hmm.
and then it started to evolve from that.
Well, okay, so you developed a synthetic tracking algorithm. What were
Yes.
some of your challenges developing that?
Well, it turns out for me, detecting the objects and that was only part of the story. That was only part of the problem. So okay, you have a detection. Great. Now what do you do with it? So I have the pixel coordinates. Well, now I got to learn how to do astrometry. Okay. So all my program did at the time, very early on, is it just told you that, oh, here's an object that has motion.
Okay.
And it could be a very faint object. That's the idea with synthetic tracking, is it allows you to detect objects that are at the noise floor, basically. So you can detect these very faint objects, but at the time, it was just very primitive. And so one of the challenges was I had to learn how to do astrometry. So load a star catalog, do plate solving, convert from pixel coordinates to sky coordinates, all of that. So that was the next phase of making it a useful program. So
Wow.
yeah.
So, uh, okay, so when you hear that Tycho has discovered 200 objects, numerous comets, how does that make you feel?
Well, it is pretty cool actually.
Yeah.
It's pretty cool that it's kind of used by others. Like it's pretty cool to create something and have it have others find it useful. So
Hmm.
I do like seeing that and being able to improve um, on it and keep on delivering useful features. It's rewarding, I would say.
Good. How user-friendly is the software?
Well, I try to make it as user-friendly as possible. Now, that being said, there's a lot of functionality that, the learning curve, it depends on if you've never done, uh, astronomy or just the basic, there's going to be some learning curve involved.
Hmm.
So if you're not familiar with asteroids, now having said that, I have put together a lot of tutorials and user guide
Hmm.
on how to use it. So there's a step-by-step guide that kind of walks you through the basic scenarios. So just a quick start, here's it. In fact, I even provide some example data sets. So you can go on to the Tycho website and download an example data set.
Okay.
And
Yeah, I've seen that. Yeah.
yeah.
So, where have you seen where newcomers struggle most with using the software when they're first getting started?
Well, to be honest, I don't know that there's really one primary point
Okay.
of struggle with it. I think that there's just various, I think for the most part, I don't receive a huge amount of email on, oh, I couldn't figure this
Okay.
out. They usually tend to figure it out on their own. So that's, I think that's helpful that a lot of the people that use the software to start with are fairly knowledgeable to begin
Right.
with. So but there's the occasional, okay, I couldn't plate solve this image. Maybe you can help me with that. And that's fine. That's, nothing, but for the most part, it's pretty, I'll get some questions like, would this graphics card work with Tycho or something like that,
Yeah.
so,
What type of system, is there a minimum requirement for the system to run on?
well, so that's a great question. As far as a minimum system requirement. I believe I do list that somewhere in the user guide, but like I've recommended. So if you want to use synthetic tracker capability, then you would ideally want to have a GPU. It does actually work without, but it's going to be slow.
Okay.
So I would recommend just a reasonable, it doesn't have to be a high-end GPU, but just something that's, today I'm still using a 5-year-old GPU from 2020 and it still runs great.
Okay.
And so any modern GPU, in fact, I was just researching this a while ago And today you can get a NVIDIA 5060 Ti that's 3 times more powerful than what I bought 5 years ago for the same price.
Yeah.
So I
Yeah.
mean, so
Yeah.
they've come a long way. Um, yeah.
So
Um,
is there a particular success story you'd like to share, that one of your favorites?
well, I mean, I've got a few, but I mentioned Catalina Sky Survey
Hmm.
earlier, so they've been using it not for discovery necessarily because they've got a massive
Hmm.
sky that's for that, but they do actually use it for recovery.
Oh, okay.
And so the way that works is they might discover a new asteroid, and okay, they've got just one night of observations. So it's a very short arc. And if they don't follow it up soon, it gets lost.
Hmm.
And so with that short arc, there's a lot of uncertainty baked into what its orbit will actually be. So they have used it on a number of occasions to recover those single night discoveries that they've actually would have lost otherwise. So there's been over a dozen asteroids I've been told that they would have lost without the use of Tycho. So
Okay.
I thought that was kind of cool.
Okay. Now, did you just recently add photometry to the capability of the software?
No, that would astrometry, if I understand your question correctly. So yeah, astrometry, I added that. That was still in the 2018, 2019 time frame. So that
But
was still
what,
early on.
okay, but what about photometry, measuring the brightness
Oh,
of?
photometry, yes.
Yes.
I added that probably, I want to say in 2020.
Oh, okay.
Um, and so that was, yeah, still, for a while, it was purely just, oh, I can discover an asteroid and now I can generate astrometry measurements. And then I did, a couple of years later, add in photometry. So,
So it's become quite a useful tool for a lot of astronomers in asteroids and variable stars, I gather.
yes, I believe so. Yes.
Okay. Would you like to do a demo of the software?
Sure, I can do that.
Okay.
So I've got, before I do it, I have just a few slides I can also share too to
Okay.
kind of walk through what I might demo. So let me see if I can share. This is always the fun part, trying to figure out how to share my screen here. So let's take a look here. All right. Okay, are you able to
Yep.
see? Okay. So I've just got a few slides here, and so just a brief overview. We've kind of talked about a few of these points,
Hmm.
but I wanted to kind of highlight for the demo. Okay, so I mentioned a little bit about, and we've kind of touched on it, synthetic tracking.
Hmm.
So yeah, that's where we can take in a set of images and do hundreds or thousands of different motion vectors to find a faint object. So you can typically do 10 times fainter than what you would with what I call the conventional method. So yeah, let's go ahead and see here. Yeah, I mentioned some of the statistics, so two impact, so all that. One thing that is kind of cool. So there's actually this article in Nature. They released an article earlier this year where James Webb Space Telescope. They had actually used Tycho, and they discovered over 138 what they call decameter size asteroids. So these are the really, really small asteroids that were discovered using the synthetic tracking tool of Tycho.
Wow.
So I thought that was kind of cool.
That is kind of cool.
Yeah, yeah. Um, so, okay, let's go ahead and get to the demo here. So one of the points here is I've got one that I can show images of OSIRIS-REx.
Hmm.
So if you remember that one in 2023, it did a return, and I believe it was in September of 23.
Right.
And so they first went out to asteroid Bennu. They did a sample capture, and then they had a return, which
Hmm.
I love this. This was a
Hmm.
really cool thing that happened. And so I happened to take some photos of it or images that, let's see if I can go ahead and So if you see this, are you
Yep.
able to see the, okay. So let me share that real quick. So the first one here, this is with again, I rented some time on a telescope and took these images. So if I, yeah, I can do the maximum stack here. So
Okay,
this is
this is
just
a this is a
combining.
Banu, right?
This would be actually the sample return.
Okay. Oh,
So I took images of, you can actually start to see it here. If I zoom in, you see one track, right? So
hmm
just a dash, and then you start to see two tracks.
Okay.
And what that is you're actually seeing the main spacecraft, and then
Huh.
the feiner is the sample return capsule.
Oh my
And
goodness.
so you can start to see them diverge, and I just thought that was really cool.
That is,
That and so I can also animate the frames here a little bit, and you can see as I do that
hmm
this separation. So this isn't really anything specific to Tycho, but I thought it would be an interesting thing to share.
Yeah.
Uh, and so that this is these images were taken with a 20-inch telescope,
Okay.
so or half meter if we want to use those units. And so I also just have another one. This is with a 5-inch, 127 millimeter telescope. Same kind of situation. And the question is, can we actually see it with this smaller telescope? So you do see the main spacecraft here,
hmm
the brighter
hmm
line, and you can just barely tease out
Oh yeah.
the feiner. So I thought that was pretty cool. This with this even a smaller telescope, you could see this separation between the two.
Hmm.
So, okay, that's one demo. I wanted to show a little bit of the synthetic tracker. So um, this is actually one of the sample data sets that you could download from the Tycho website.
Okay.
So this is a 2 hour total exposure time, 60 images. They're 2 minutes each. And so the basic way it works is, okay, you've loaded your images, and then you can go to synthetic tracker, and I always just use 50% threshold as a starting point, but it's adjustable. And for this really uh, brief demo, we'll just do a main belt asteroid. So what that means is main belt asteroids typically have a common speed and position angle range. So zero point 0.2 to zero point 0.8 arc seconds per minute, and 2 to 300 degrees for the position angle. So what it's telling us here is that if we do that kind of search, it's going to do about 1,500 motion vectors. So I click OK. And so this is running on my GPU here, and we give it a moment, and it's already completed.
Hmm.
So this is just a basic search, and we can tell it, okay, I've got this list of candidates returned, and it has computed the confidence. Now we want to know what these are. So we can do load known objects, and it says, okay, after a moment, here are the identified objects. So you can see a lot of these are known objects. So I
Okay.
can click through here. And so like the first one, I can double click on it and I get an animation.
Right.
So I can do median stack, or if I want, I can do an average stack like this. Um, Now I can also see, oh, here's number 14. It did not match with a known object. So let's see what that looks like. So I double click on that, and it does appear to be a real object. It's
hmm
faint, but it does appear to be, uh, potentially a real object. So that's how you would potentially use the synthetic tracker for discovery is you give it a field, a list of images, and it does the search, and then you're presented with a list, and anything that does not match with a known object, you might pursue that further, especially if it has high confidence. Now, I will say this, for a beginning observer, there are some tips I can offer. One is if you are interested in doing discovery, well, you would ideally want not just large aperture. That's certainly nice to have, but you don't want to be looking through a straw.
Yeah.
You want wide field of view. And so what's nice about modern advances today is we have the RASA / Hyperstar type telescopes. So the Roe Ackerman Schmidt astrograph or Hyperstar, those are great tools. They have wide field of view and a decent amount of aperture. So yeah, I would also say we've also had, this has been very, very fortunate. We also have modern CMOS sensors that, very low readout noise, so you can take these shorter exposures, and those are great in conjunction with synthetic tracking. Another tip would be, okay, I think you mentioned earlier about false positives. How could we reduce false positives in one of your exchanges? And again, the suggestion there would be you would ideally want to dither the exposures. So that introduces a bit of random motion that any kind of camera artifact like a hot pixel, it would no longer form a linear track
Okay.
if you have dithering. So, and also, if you can eliminate the hot pixel to start with, so if you have a good dark frame, that's always recommended. So anyway, this is just a one demo here on the synthetic tracker. Now I mentioned recovery, and what that looks like is, suppose we have a known object. So let's suppose this is our known object here, 2000 RZ92. Okay, and so pretending if I were that I just done a discovery of that object, I could, lots of different ways I could do this, but I could attach ephemeris of that object. So JPL Horizons, I'm not sure if you may know of their service, but they have a fantastic API that you can query. And one of the components of that is you can look up an object. So by number, designation, or name. So in this case, we can supply it the designation of this asteroid, and I can attach it to the data set. And so what that does for us is we now have all of this ephemeris information for each and every single image for that object. So I have the speed, position angle, the magnitude, alt azimuth, and so forth. Now, again, the scenario here that I'm presenting is we're pretending as though we just discovered this object the night before, and we have a rough idea of where it might be. So I can do the synthetic tracker, and I can say, okay, use dataset ephemeris. And what that does for us is it limits the speed and position angle to narrow down to what the motion of the object it thinks will be. Now, you can obviously expand this later on if you have higher uncertainty in the orbit, but this would take, from a discovery search, which, to be honest, you would typically want to widen it more than I showed earlier. You wouldn't want to just search for main belt. You'd want, so it would take a normal search of 20 minutes. Now it's this quick, right? It's almost instantaneous.
Wow.
So, so again, we can load known objects and go through the process. And you can see that 2000 RZ92 is one of the objects listed. So that would be an example of a recovery. It's the same thing, but you've tightened the search parameters.
Interesting.
Huh.
So go on.
Go ahead.
No, go on.
Okay. Well, I was just going to show another demo.
Okay.
But if you have a question, I can.
No, I want to go into light curves too, but
okay.
See what else you got here.
All right. So another demo. Yes, that's perfect timing. I do have a light curve demo here. So this is an asteroid 1627 Ivar is the name of it. And so this is actually, I mentioned the previous data set was 2 hours. This one is just 4 minutes total exposure time, but it is over 5.3 hours. So these are really short exposures, 2 seconds each.
Oh my.
Over 5.3 hours. So let's see what that looks like. So this is the object of interest. And the way you can tell that is I can stack the images here. So this is the average stack. You can see the motion. So lots of different ways to do photometry. The user guide goes into that quite a bit, actually. And I've got a lot of tutorials on it as well. The basic process is you have your star catalog. then you set your apertures, and then you find the optimal comparison stars. So there is a comp star finder module in Tycho, so you can go to photometry, find comp stars. And this will present you comparison stars that meet your criteria. So min and max magnitude, the color of the star, if you want solar color stars, and minimum SNR. So you can put in a filter, that is what I'm getting at. And then you can click on these different candidates and identify if those would be desirable comparison stars. Now, I want to show you just real quickly, let's suppose we don't do that. Let's suppose we just do a really quick automatic comparison stars. Let's see what kind of result we get with that. So again, the asteroid in question is right here. And if I zoom in, here's the first position of it. So I can create marker number 1. This is one of several different ways to do this. So we're just defining the motion of the object. And I can scroll down to, let's say right here, it doesn't have to be the last image, but create marker 2. So we've now defined the motion of the object. And I'll go ahead and set the aperture settings here. So if I zoom in here, you can see the inner radius, and I might choose that, and then the dead zone and sky annulus. So these are the different settings you can choose for aperture.
Okay.
And again, I just mentioned if we want a really quick test, I can go ahead and create the data points. So I can choose create photometry from markers. And you can see here it's working through this set of images, and we now have this light curve.
Wow.
So that's pretty quick. Now again, but I cheated a little bit because I'm using what I call automatic comparison stars. So again, if you're doing this for a more professional grade, you would want to use the comp star finder, and you can choose your comp stars. So if I do that here, I can right click and choose multiple comp stars. I typically do between 5 to 7. And this is also going to show you the variability of that comparison star. So you would not want, for example, a variable star as your
right.
comp stars. So that's the basic idea. And again, I can take this in more depth as well. But just for a basic demo, this is our light curve, and we can also do rotation period. So I can say, okay, here's the start and stop condition. If I'm not sure what the actual rotation period is, 0.1 to 20 hours, that's a wide range. Click find period. And I've got a list of candidate periods returned here. So it says 4.7. Now, if you're not sure, some of these do have published rotation periods. So I can type in 1627. That's the number of this asteroid. And it says the rotation period is 4.795. And so we said 4.724. Now that's, with one night of data, that's not bad. So that's a pretty good match for a single night of data. So that's a really basic light curve example.
Okay. But your accuracy increases when you select your comparison stars yourself.
Yes, generally that's what I was trying to get at earlier. Yes,
Right.
is when I say I cheated earlier, that's because I was being lazy and just choosing the automatic comparison stars, which for a really quick look at the light curve, that's okay.
Okay.
That's okay. But yes, you can generally get better accuracy, if you will, using a curated list of comparison stars that you use the comp star finder, and you have this filter that show me only solar color stars, and as a first pass, and then I can look through and see, okay, is this is it adjacent to a hot pixel or other camera artifact or what have you, right? So as you click on these, it'll center on the star, and you can say, okay, do I want that or not? So absolutely, you can get a little bit more accuracy using
Okay.
the manual comp stars.
Okay. Yeah. Now, estimated comet magnitudes have always been, there's a lot of inaccuracies in that depending on the method of using. How accurate is this for working on comets?
Well, that's a great question. I actually recently added a module for comet photometry, and so if you're interested, I can show
Yes.
a
If you,
brief demo on that. So
yeah.
we do have a comet. Let's see here, 2025 K1, and
Very
so
good.
let's see what that looks like. Um, so. Uh, here's the object. So
Hmm.
this is a very crowded star field. So
Hmm.
that would be one challenge right off the bat. But what this module allows you to do is you can say, I have, first of all, my star image. So this would be the image where I can just go ahead and here's a stack of my images here. And I can say, okay, I might want the median stack. So the median stack will filter out the moving object you see. So now I have just the stars. And so I can set that as my star image. And then it wants the comet image. Okay. So again, I mentioned this is uh, C2025K1.
Hmm.
I can attach that ephemeris to the data set. And it's asking me, okay, which one is it? There's been a number of fragments of
Right.
comets.
Right. Right.
So I'm just going to choose this one here, select record. And now the one issue is I need to understand what observatory took these images. So it's going to compute the ephemeris based on whatever your observatory setting is. So let's go ahead and see how accurate this was. This was accurate enough. So if this were a faster moving object, I'd probably want to update my observatory settings. But for this example, let's go ahead and work with that. So I can select, um, let's see here, do a selection. And here would be my comet image.
Okay.
Okay. So we basically with this, we've stacked on the motion of the object. And now you can see that we've kind of filtered out, if you will, a lot of the stars in the field in this fashion. So this is the comet image. And now I specify the comet origin. So that just means I center on the object here and I choose apply from image viewer. And so it already took in, when I attached the ephemeris from JPL Horizons, it already recognized, okay, this is the comet, here's the name,
Mm.
comet Earth distance, comet sun distance. So we have those parameters. And now I can say also what aperture settings I might want to use on this object. So just depending on uh, what you think would properly enclose the main core of it. Uh, Another astronomer recommends kind of increasing the contrast a little bit.
Oh, okay.
And you can do that. So let's see what this looks like. So I can choose, first of all, again, this is a bit more of a detailed demo, but again,
Hmm.
you can select comparison stars. Let's see what we have with this. Lots of comparison stars because this is a very crowded field of view.
Right. Right.
But let's go ahead and tone down the max magnitude here and maybe even, let's see what this looks like. So, okay, and I want to do this with the star image. So the trick here will be to find comparison stars that are not too close to other, that have a nice clean signal. So let's see if we can find some uh, in this example. So uh, again, I might choose this and I can update the aperture for that. So I know I'm going really, really quick through this example, but bear with me for a moment.
Hmm.
We'll see if we can get just see what the result looks like. So I'm going to choose, like I say, I typically do between 5 and 7
Okay.
comparison stars. And let's see if I can add a few more there we go. So I have my list of comparison stars here, and I can generate data and I can look and see, okay, maybe I don't want this last one, so I can remove that. Um, so we've updated the comparison star aperture. We also have the comparison stars chosen, and I can just, let's go ahead and see what the report looks like. So here we have now, this is what you would typically see with comet photometry. The magnitude is the red line here, and then what they call afro in centimeters or dust production rate. Um, and so you get this report, and it also provides you the ICQ line. I don't know
Oh
if you're
my.
familiar with that.
Yeah, yeah.
Okay, but it generates that as part of the report, and so you can actually then submit that as a measurement. So
It's all done in the right format.
it is, yes.
Wow.
And so yeah, like I say, I mean, an example like this, if I were wanting to do it more carefully, it would take me a little bit more than we have time for this,
No, I
you know.
understand.
But I just kind of walk through the basic steps here, and you can kind of get an idea of what that looks like. So I believe the question was, how accurate is it with comet photometry? And so I've been working pretty closely with another astronomer who maintains the COBS website. Uh, Maybe you're familiar with that or not, but he has vetted it and said that it's very much within zero point 0.1 mag, typically, of what he has seen with his results. Um, so part of it will be observer, part of it,
Hmm. Hmm.
hopefully the tool won't be the main, culprit, but it's at this point it's gone through the process and validation that we can say, that the tool appears to be producing what we expect it to. So again, there are a lot of different knobs you can turn, like you say,
Hmm.
when it comes to what size aperture you use, that will have an impact. But yeah,
Yeah.
so um,
How many users do you currently have of the software?
right now over 1,500.
Wow,
So
that's great. Now, are you still making changes, added developments to it? What were some things we could look forward in the future?
yes, so last year I added a new module that's a little bit different than synthetic tracking, and I call it Fast Tracker. This stands for Fast Acquisition of Streak Targets. Last year I bought one of those C-star telescopes.
Oh yeah,
I'm sure you've heard of that.
got
And
one.
okay. And I bought it because I was curious to know what could I do with my backyard, sky. So I went in with really low expectations, and I was actually pleasantly surprised
Hmm.
at what I could see with it. And so I actually even did a light curve of an asteroid with the sea star. So this is one of the brighter asteroids, of course, but
Hmm.
it was still enough that it's like, wow, I can figure out the rotation period of an asteroid using this small telescope. Um, so so I thought that was pretty cool. But back to my the new feature here. While I was going through those images of the sea star, I noticed, now here's some streaked objects, artificial satellites. And I thought, well, wouldn't it be cool if I could have Tycho just tell me what those objects are, right? And if I could load it these images and it could tell me what those streaked objects are, and actually go a step further. It's one thing if you just have a database of known artificial satellites, that's nice. But could it find, just generally speaking, any streaked object, even if it's not known, things like that. And
Chances are it's
so
Starlink.
chances are it's Starlink, but all those are known,
Yeah.
so it'll identify those pretty easily. But yes, so if you want, I can show you just a quick
Yeah.
example of that. Okay. So here's one of those demos. This is actually of, if you're familiar with the advanced solar sail, I'm forgetting the third, ACS3.
Hmm.
Okay. In fact, let me bring up this is what that looks like, right?
Right.
So Advanced Composite Solar Cell System. Okay. So NASA, they put this together and launched it as a prototype. And so I happened to image that. And so the main point of that demo is, uh, not just, oh, here's the solar sail, but can this, what I call fast tracker, can it find it? Because with synthetic tracking, one of the trade-offs is that the object has to be in the images 50% of the time or more. And you might ask, well, why is that the case? Well, that's because synthetic tracking is doing a median stack on the images, okay? And so, if it's present less than half the time, it's not going to survive the median stack. All right. Now, for asteroids in your field of view, that's usually not a problem, but for fast-moving objects, it can be, right?
Hmm.
So anyway, that's what Fast Tracker does. Is
Okay.
it can make use of it can find objects that are not necessarily in the field of view the whole time. So let's do Fast Tracker, and it's going to, you have some knobs you can turn just like with Synthetic Tracker,
Right.
but
Right.
I pretty much always just do the standard and click OK. So I've got 171 images here. They're 0.3 seconds each, and it's already processed them. So it's pretty fast, right?
Jeez.
And so it found one object, in this set of images, and here it is. And the question is, well, gee, what could that be? So I ask it, match artificial satellites. So I can match asteroids and comets if I want to, but I can also match it with artificial satellites. So I ask it to do that, and after a few seconds, it is, okay. So this is where I do need to have the observatory setting update. So it found a match, but it said, well, that's actually a pretty bad match because the offsets are high.
Okay.
It's actually good for a demo, right? Because
Hmm.
here you have an example of here how you can fix that. I go into my observatory setting, I say, okay, I need to set it to the observatory that captured these images. All right, so let's try it one more time. And here we go, ACS3. All right,
Wow.
so now you can see much lower offsets. So now you have confidence that this is a good match. The distance is correct and the long track is nice. So object name ACS3, that is the object of interest right here. So it's pretty quick, and assuming you have the right observatory setting, it will correctly identify the object. So that's what we've done here. And so it's pretty cool. And so you can use it for both artificial satellites and asteroids. It's it's another nice to have feature
Hmm.
in Tycho. So that's a recent thing I added. That's kind of cool. And so I've also taken it a step further, and you can actually add the object. I call it TLE propagator. And what that means is I can actually do a view of this satellite. So here's a satellite viewer, and I can actually see, oh, here it is. And so this is the orbit of that object. And so I can tell it, okay, start date of now, and then let me do a refresh on that. And so here we are. This is where the object is right now. And so, and I can also adjust it. So I can, here's where it would be 1.6 hours from now and so forth.
Now,
So,
where is this something you programmed, or is this data you're taking from someplace else?
so the data, uh, all of these objects have what's called a two-line element. So
Okay.
that defines the orbital elements of the object. So that data is publicly available,
Okay.
and you can retrieve that. So once you have the orbital elements, then you can integrate those elements to that's what's called propagation. You can propagate the elements to a particular time, and so that data I do have. I don't generate that myself, but you could generate it yourself actually from observations. So if you were to take
Hmm.
in, and Tycho lets you do that too. You can say, oh, here's I found this object in one night, made some measurements, and Tycho will generate a two-line element for you. So that's kind of cool. But
Okay.
yes, to answer your question, I did write this viewer myself. It's part of Tycho, and it works on both the Mac and Windows version as well.
Wow.
So it's a nice way if you wanted to, and you can also do multiple satellites at a time. So here's multiple satellites that you can look at. So we have some Navstar GPS satellites,
Okay.
Galileo, and so forth.
Wow.
So I keep adding little new features here and there that I think others might find interesting, but
Yeah. Watching you zip through this, I know you're the developer of it, so it's like your second language.
well, right.
Um, are there plans to automate any of these processes or actually use AI to
Right.
make it a little more
Uh,
intuitive?
so I took a stab at automating a few years back with the what I call auto run. That's part of the scripting. I call it, auto run. And what that does is just briefly, I can show you settings. If you go to the settings menu, you can. It's based off of a few different passes that you do. So we talk about data reduction first. So we do calibration of images, so dark frame subtraction, flat
Mhm.
building, all that stuff you can do up front. So this is what's called express mode. So you can choose different things here. So you do calibration, plate solving, alignment. And then once you've done that, then you can choose to run the tracker on that, either the synthetic tracker or the fast tracker that I just showed. And then it will generate the results and save those. So the auto run module, you can generate a batch script. And this is what a few others have done with Tycho is they do run it in an automated fashion. In fact, the Catalina Sky Survey example I gave earlier with the recovery, they do have a pipeline that they use. They can say, here's a directory of images. Tell me if you find it or not, right?
Hmm.
So they've been able to automate it to that point, which is pretty nice. And so there are tools to automate with Tycho. The user guide does go into some detail on that as well. So you basically can say, here's my directory of images, do calibration, do alignment, do plate solving, do the tracker, have at it, right? So you can automate with it. Now, the other question was AI with Tycho. I don't have anything, well, AI built in, if you will, in that
Hmm.
sense. Now, and so that might be something that could be looked at, what, um, you know, how to integrate that. I'd have to look and see
Hmm.
which scenarios that might make sense. Yeah.
Okay. All right. Yeah, it seems like there's a lot of professional collaboration with you already too,
Mhm.
with Osiris Rex and Catalina Sky Survey. So that's
Sure.
that's quite a feather in your cap to have them using your software.
Right.
I have Carl Hergen or other on the podcast quite frequently, and he helped develop the Catalina Sky Survey.
Oh, really?
Yeah,
Okay.
and he's our comets coordinator for the Alpo. So yeah, we talk to stuff all the time.
Oh,
Crazy.
excellent. Excellent.
Yeah. So if so now, how many versions of the software is it, or is it one package that you download?
Well, as far as the version is concerned, it's at version 12 right now.
Yeah.
And so, um, and
Does that include everything?
well, there's two different, okay, so that would be like the version number. Now there are two different variants of the software. There's a standard version of it, and then there's a pro version. And so pro version is everything. It includes the automation I talked about earlier, so the scripting part. Standard is for what generally most people might use, but I typically see most people go for the pro version because it does have a few extra nice features.
And the
So
cost isn't that different. Really, it's not, was it?
not it's $25 different. Yeah.
Yeah, that's okay. For the software. Why didn't you get
Right.
into gaming, dude? You'd be making some real bank.
Right. Right. Yeah. Yeah.
Wow. So if someone wanted to get started with it, and you have a lot of demos that come along with the software that they can learn with, but is there like a good first target object or objects you would recommend they try
Well,
for their own
it,
data?
yeah, so it kind of depends what their goal is. If their goal is discovery, then the recommendation there would be, okay, point your telescope at the ecliptic or near the ecliptic, where most asteroids are going to be located, just to reinforce that, okay, you are getting some moving objects in your field of view and calibrate, make sure that things are working, right? So it's just the very basic steps there. Um, and so that would be a first recommendation, is to just try some known objects as well. So and then once you've done that, then you can venture on your own, so to speak.
Okay. Um, what's one feature that you've asked to implement that you don't want to implement or you can't?
Mm, I can't really think of one yet, that I've been asked and have not. There might have been a few esoteric things that, it's like, well, here would be a feature that's it's a really special case that maybe one astronomer might
Okay.
find useful, and it would take me a lot of work to develop it. And I if I finish everything else on my plate, maybe I'll get around to that. That kind of feature, right?
Okay.
Um, so, but I typically like to go for features that more than one person would find useful. So,
Okay.
uh, but yeah,
So if you had to design your own imaging setup, what would it be?
my own imaging setup.
Ideal. Dream.
Like from the hardware as well, or just oh well. Again, it depends on the objective. If the goal is survey, then I would want to have an array of telescopes, and that's something I pointed out in one of the papers I wrote on the topic was, for the cost of, you look at telescope aperture, right, and it goes exponential in cost. But if you have, an array of smaller telescopes, that can actually be competitive, with synthetic tracking because now, okay, they're smaller aperture, but if you use synthetic tracking, then they can kind of compete with those, larger aperture telescopes.
I
And
see people
that,
doing that with a series of sea stars. They're linking
well,
this.
okay, yeah, that's true. That's true.
Yeah,
Um,
that's
so yeah, so I mean, that would be one way to look at it. If I were focused more on, maybe variable stars or something like that, then it might just be one nice telescope, that's optimized for that. So,
okay. So are asteroids though your passion? Probably.
well, they are anything that moves. I kind of, or something like that is, like the artificial satellites. That's kind of cool. I'm actually I just finished a paper also on another way to compute, or do orbit, initial orbit determination. So that's another feature in Tycho I'll be adding too. So.
Are you a student or are you a graduate student or what?
So I am not a student anymore.
Okay.
I'm in the workplace, and
Okay.
but yeah, I've written, when I say write papers, these are more just, I see that maybe they're doing a conference, so I can
Hmm.
submit a paper to a conference and, um, that sort of thing.
Okay. Where in the country are you located?
I'm here in Oklahoma City,
Oh,
so
okay.
yeah,
All right.
so yeah.
How are the skies?
Well, like I say, they would probably be better if I were not here in the
Oklahoma City.
near the yeah. So, yes, they're not terrible.
Okay.
They're not bad. I like I say, I was pleasantly surprised when I tried out the Sea Star in the backyard. Went in with really low expectations, but it was pretty cool to see what it could do.
Yeah, I'm impressed with the little telescope. I just,
Hmm.
I set up on my patio and I go inside and watch TV, and then my iPad be sitting there watching it download images. It's
Yes,
it's
it's
amazing.
it's
So
pretty slick.
if someone were to get your software, what's one tip would you give them that would instantly improve their results?
That's a good question. Well, it, it- I know I keep saying this, but again, it depends on what they're trying to do. But
Okay, all right,
if
fair.
they're doing if they are doing synthetic tracker, for example, and they say, "Oh, hey Daniel, it tells me it's going to take 20 hours to finish the search." Well, usually that's down to a couple of things, but one is they might have a very long dwell time on a field that's just not necessary. So maybe they gave it, um, you know, 5 or 6 hours of that's um, for a particularly fast object. So if it's a near-Earth asteroid, for example, it's a fast mover. You don't want 5 hours of total dwell time on that. You might do 10, 15, 20 minutes on a near-Earth asteroid. Um, and the reason I bring that up is because, yeah, if you have a long dwell time, it has to search, it goes up quadratically. So it has to do both X and Y axis, if you will, on the search grid. And so you're looking at a noticeable increase in computation time. So that'd be one suggestion. If you see a long, oh, it says it's going to take 20 hours, it doesn't have to. It doesn't have to. You might want to rethink if it's a fast moving object, take a set of images that are optimized for that.
Okay.
Now, if it's a slow mover, sure, you can even do potentially multiple nights of data. But I very rarely do, even with main belt asteroids, I very rarely do more than a couple hours of total dwell time. So,
Okay.
yeah.
So are you working on a project with their system now, estimates, rotations, something like that? Or are you still tinkering with the software, trying to fine tune it a little bit more, or both?
When you say the first part, am I working on like another type of project or?
No, do you have an observation program?
Oh, do I have my own observation program?
Yeah.
No, not myself, although I have collaborated with other observation programs.
Okay.
In fact, the slide deck I had up earlier, there were two amateur astronomers I collaborate with. That one of them is in Alabama,
Hmm.
and he has found over 80 discoveries on his own with Tycho. And so he has two C14 hyperstars, and so he's got a nice
Oh, he's
setup.
got the equipment.
Yeah, he's got the equipment. Yeah. So he's done quite well with it. And then I am also part of the MAP survey. It stands for Murray Parrott, and then we recently added another member, that Florian Signer. I can pronounce the last name, but we so the MAP survey is in Atacama, uh, Chile. So
Okay.
they have quite a nice.
The
They do
remote
have
telescopes down there.
they do have nice skies
Yeah.
down there. Yeah.
Using
So
the remote telescopes down there.
well, Murray actually has his own. He operates his own astronomy tour business
Oh,
actually,
okay. Hmm.
and so he does operate the telescopes there physically.
Great.
So, yeah.
Great. So is there anything you'd like to share with our audience before we close
Well,
up?
just I think we've gone through the most of the familiarization of Tycho, but sure, I could share. If they're interested in the website, tychotracker.com is the website, and it has a download link. And like I say, there's several data sets available there for download and experimentation. So,
Yeah, I will add all those links to the show notes for
sure.
anybody interested. Great. Well, Daniel, this has been great. I've been looking forward to having you on the podcast, and finally we
Well,
made it happen.
it's been a pleasure. Thank you, Tim.
All right, thank you.
Thank you.
All right, that's a wrap for this episode of the Observer's Notebook podcast. A special thank you to Daniel Parrott for joining us today and sharing his insights on the Tycho Tracker software. If you enjoyed the episode, please take a moment to give us a thumbs up, subscribe, and share with the podcast. It really helps reach more listeners. New episodes of the Observer's Notebook are released every few weeks. You can find us on iTunes, Spotify, and the ALPO YouTube channel. If you'd like to help support the podcast, you can do so through Patreon for as little as a few dollars a month. Up to $35, where you receive exclusive benefits, including one-year membership to the Association of Lunar and Planetary Observers and producer credits right here on the show. You'll find links to our Patreon page and the ALPO website in the show notes. A special thank you, as always, to our producers, Steve Siedentop and Michael Moyer, for their continuous support of the Observer's Notebook. And if you'd like to reach me, you can email me at tim.robertson@alpo-astronomy.org. Thanks for tuning in. You can join the Association of Lunar and Planetary Observers today. It's just this easy. You can become a valuable member of this International Lunar and Planetary Astronomy Organization, founded in 1947 by Walter H. Haas. It's based upon the structure of the British Astronomical Association. You can join various lunar and planetary observing sections, contribute to our massive archive of observations. You'll have access to our extensive lunar and planetary gallery of over 20,000 photos and observations of the sun, the moon, comets, meteors, and the planets. You'll receive our quarterly publication, the Journal of the Association of Lunar and Planetary Observers. You'll have the ability to join the ALPO training program, which will teach you the finer points of making planetary observations. You can attend our annual virtual conference, and you'll have access to the Observer's Notebook podcast. Membership begins at only $22 a year. The way to find us, just go to your Google and type in ALPO Astronomy, and you'll see this prompt come up. There's our association with our website, alpo-astronomy.org, and you'll come to our homepage. If you look at the top of the homepage, it says Join ALPO. Click on that, and you'll come to the sign-up screen. Gives you the information on the organization, and there's two ways to join. You can join by mail, where you'll download a membership form, or you can pay online using PayPal. This is the PayPal processing page. You just fill out a few information lines, and then you're given the chance to click PayPal and join the association. Welcome to the ALPO.